Hello again. We are now in chapter 8 that has to do with optimization of hyperparameters. Hyperparameters in machine learning are the parameters that we set for a model that don't change during the learning. We have to set them and then do the learning, the training, and we need to somehow select the best hyperparameters, and this is done by trying different combinations. In our case, we will look at a classifier, Adabus classifier, that has a certain hyperparameter. This is the documentation from scikit-learn. So it has various hyperparameters that we can choose. Some of them are binary, just this or that. Some of them are integers, some of them are floats. We will concentrate on three particular hyperparameters, and we will try to train this model on a problem that's called the wine dataset, which is a classification problem, and see how well we can select those hyperparameters. So in choosing the hyperparameter set of values for a model, two common methods are grid search and random search, where in a grid search we go over certain fixed values for each one of the parameters, and then we try all the combinations. So we have here in chapter 8 a problem that the first program is going to run a grid search on the three hyperparameters, and here we see the hyperparameter values that we're going to try. The first one will have 10 values, the second one has also 10 values from basically 0.1 to 1 learning rate, but logarithmically spaced, and then the algorithm has two values, so altogether we have 200 combinations of these parameters, and the grid search will go and search all the combinations and find the one that yielded the best results, which in this case we measure accuracy of the model in classification using cross-validation. Then the same program will continue and will use a genetic search that only that searches on those combinations, but tries to make a smarter search rather than go over all the combinations or just go over random combinations, which is the random search. It will try to use genetic approach to find the better combinations quicker instead of using brute force or random. So we will be able to compare those two methods when we run this program. So let's run this. And this can take a while because grid search by nature is sort of slow. It tries all the combinations, and for each combination we need to evaluate, we need to train the model and then evaluate it, and then at the end, after we finish all the 200 combinations in this case, we will see which was the best, and that will be printed. And as you see here, there is also a score with default values. The model, as you can see here, has default values for all the parameters, what we see here, like 50 estimators, learning rate 1, etc. So the performance of the model with these values is what we call a default, and it's not so great. It's 66% accuracy. So the grid search is continuing, and it's trying to find something that from the combinations that are possible in the grid that we defined, it tries to find the best combination. So we're going to wait for it to find the result. So here is the result, and the grid search has concluded and found these to be the best values out of the grid that was defined. And indeed, the accuracy here with this set of values is 92.6 or 92.7%, which is way better than the default values. And it took 92 seconds on this particular computer that I'm running it on. And now, while I was talking, the genetic grid search was running, And as we said, the genetic grid search is searching exactly the same combinations, but in a smarter way, in a genetic way, where it tries to get better and better over the generations. And we only run it here for 5 generations with 20 individuals. And we see that it found the exact result. It found the best set of, the best combination of parameters out of the grid. And the same performance with the 90, obviously the same performance, 92.7 accuracy, but the time is way shorter. So here it took sort of just under 17 seconds versus the 93 seconds that the grid search, the exhaustive brute force grid search was able to do. So this shows one use of genetic algorithms where you have a set of combinations, and instead of searching all of them, instead of trying all of them, you will search in a genetic way on those combinations. But maybe there are even better choices that are not on the grid that we define. Maybe they are between the points of the grid. So we have another program here. The second program is actually going to search over all the values that are possible over those ranges that we define. So the range will be 1 to 100, 0.1, 0.01 to 1, and 0 and 1 for these 3 parameters, where the 0, 1 basically is translated to the binary choice of the 2 kinds of algorithms. So if we run this, we hope to find some combination that maybe is not on the grid, but maybe give us even a better accuracy or better score for the function. So let's run this. And this will run longer because we're trying, we have more, the search space is bigger than the grid that we had before, because it includes all the values that are within the boundaries of the grid search. So we're going to let it run and see if it gives us better parameters, better accuracy. So here are the results of the genetic algorithm that we ran. Also, we only ran it with 5 generations and 30 individuals here. And we see that it found a set of, let's close this and take a look better here. So this is a set of hyperparameters that it found that is not exactly on the grid. It's sort of close to the grid, but the performance here is better. It's 94.4% or so. And it did it within 5 generations, and took less really than running the entire grid search. So in real life problems, you will usually have much larger grids, much more values and types of parameters, and using a genetic search can basically save you a lot of time. That is it for chapter 8, and we will continue with chapter 9 next.